Science at the University of Michigan in Ann Arbor. Before this, he has held appointments in the Queensland electricity supply industry and various universities in Australia and the USA. Dr. A.Hiskens' research addresses issues that arise in the design and operation of power systems using concepts from nonlinear systems, optimization, and networks. His recent activities have focused largely on integration of renewable generation and controllable load. We're very glad he could make it to our event, so please join me in welcoming Dr. Ian Hiskens.
Thank you. Okay, thank you. I'm going to talk a little bit about an activity that's consumed a reasonable amount of our time and interest lately, and that's looking at control of large numbers of loads, and doing that in a way that can aid in the responsiveness and control of power systems. There's a whole lot of different diverse people involved in various different aspects of the work that we're doing. I'll mention a couple of my graduate students up the top who are very actively involved in various different aspects of load control, collaborating with Duncan Callaway from UC Berkeley, Yongjing Ma, who was a former postdoc with me, one of Peter Kane's students who's now in Beijing. And then there's a number of guys at Los Alamos National Laboratory, physicists who have an interest or at least have funding for working in the area, and they've been a great resource as well. And then another student who was visiting from Eindhoven, and some collaboration there. So it's quite a diverse group from power systems people through physicists through control theory people, and together we're having a lot of fun discovering a lot of different ideas. So I'll give a little picture. The nature of the symposium is cyber-physical and hybrid, and my talk actually has some discontinuities associated with it as well, just to build into the whole hybrid nature of things. But I'll start off just giving a little bit of overview of where our work fits into the context, or the larger context of power systems. So this is a traditional view of the power systems. There's a good deal of activity happening at the load end, and this is where I will focus this talk. There's also activity happening in terms of wide area control. There are issues associated with both parts, both features of this enhancement that link very tightly with cyber-physical nature of the activities. In both cases, one has to deal with issues associated with communications infrastructure and how it impacts on the physical infrastructure. I've done very little work in this wide area control aspect, and will focus my attention down more at the control of loads end of activities. Okay, so why do we want to change the paradigm that's worked for a large number of years? Well, the first reason is there's an enormous amount of research funding in the area, so of course we're going to link with that. But a slightly less cynical view of life is that there's a lot of renewable generation that's coming into the grid, and there will be more and more happening over the next few years. And this figure just shows a snapshot of the variability inherent in wind power generation. So this is a 100 megawatt wind farm in Minnesota. You can see that the output is varying from 0 at certain periods in time. Well, if we look over here, it's 0, and then it's up to about 80 megawatts not that long after the 0 time, and then it's back to 0 again. So the variability is enormous, and it's something that power systems are not designed to deal with. There's a lot of rooftop solar. There's a lot of other forms of solar generation that is coming along as well, but rooftop solar is embedded in the distribution system, a system that was designed for power flow from substation out towards the loads, and now with the with renewables that are appearing within that distribution network, one has power flow in the opposite direction, and that can raise issues for voltage control and power flow control as well. And there are new types of loads that are coming into the system. This is a flash little car called a Tesla Roadster, which would be very nice to own, but of course I'm an academic, so I couldn't afford that type of thing at all. But there are other types of electric vehicles, the Chevy Volt in particular, that has hit the market, and they introduce the charging loads associated with these electric vehicles, introduce large loads that have unusual characteristics and again into the distribution system. There are disadvantages or challenges associated with these loads, but as I'll mention a little bit later, there are some advantages or opportunities that come from these loads as well. And I'll talk about that as we go along further. So the current paradigm, what we do now in power systems is that load is an exogenous input. Load is what it is. When I turn on the switch, I expect to see the electricity supply whatever appliance it happens to be that I'm wanting to turn on. Generation tracks the variations in what's going on with the loads. There's a forecast process to get the right generation on at the right time, but the forecast always has inaccuracies associated with it. No one can tell when I'm going to turn on a light switch or a dishwasher or plug in an electric vehicle for that matter at the moment. The variability inherent in renewables also creates some issues associated with deviations from forecast. And so generation has to track those variations, and that creates some issues. The generators are not designed to move around significant amounts of megawatts in a short period of time. Under the current paradigm, the voltage profile across the distribution and transmission networks is relatively constant. It's not totally constant, but it is very much predictable, and that predictability comes about from the kind of law of large numbers predictability associated with loads. Things are changing though. With increased renewable generation, the traditional generators have to be able to track these fluctuations, and so they have to be able to ramp up and ramp down, and they are ramp rate limits which prevent individual generators from moving too far too fast. So that means a large number of generators have to have availability for being able to maneuver to follow renewable changes, and that means there's generators that are kind of not being utilised fully. That's called reserve, and it's expensive to have in the system. So adding wind actually creates some extra costs for the traditional generation. It doesn't come for free as one would like to think. Distribution voltages can be quite volatile as well. There have been situations where there's a large penetration of solar photovoltaic on rooftops, on distribution systems. As the solar is producing electricity, it's pumping into the grid, the voltage goes up on the distribution network. A cloud comes along and the solar no longer produces, the voltage goes down, and so you get these fairly wild fluctuations. One can also find some interesting switching phenomena in that with a large enough amount of solar, the voltage will go sufficiently high that it exceeds the specified threshold voltage, that there's built-in protection that will trip that solar power off. So now the voltage drops low and it's allowed to come back onto the system, so it does, and so the voltage goes high and it trips off. And so you can get a switching induced limit cycle happening on distribution systems because of the increase in renewables. So these are kind of negative things that are happening as we move forward, but one of the positive things is the availability of communications and the opportunity to be able to link with a huge number of individuals in a relatively short period of time. And so it opens up the paradigm of being able to schedule or regulate or communicate at least with loads and tell them, give them some guidance in how they should respond to help the grid deal with some of these other issues. And so I'll talk about the use of this. I won't go into the details of modeling of this, the cyber infrastructure, because I don't know a lot about it yet. This is, one reason for being here is to hear what ways people are dealing with incorporating models of cyber infrastructure into the models of the physical infrastructure. It's not totally straightforward. Okay, so let me link back to the, I guess the infrastructure associated with linking loads to some control entity. This is a slide that comes from Itron Incorporated, a company that is supplying advanced metering infrastructure, or along with what people call smart meters. And I told Tom I wouldn't mention that word, but I'll do it just once. So.
Smarter meter.
So anyway.
The old meters were smart. I mean, I agree the old grid was smart, but the meter I used to have was pretty dumb.
The old meters are dumb, but that doesn't imply the new meters are smart. They're dumb in a different way. So an infrastructure, a mechanism for being able to provide this communication path is shown here. This is Itron's view. This is being implemented in Detroit Edison, Southern California Edison, and I'm sure a number of other utilities as well. At the home end, the residential end, there's a Zigbee network that is communicating between different appliances, and that communicates with the electricity meter. That meter is collecting the information from the home area network, and it's a two-way communication, so it can collect information, but theoretically can signal back out as well. A number of these meters reside in a local area network, and they communicate with a cell relay, so it's somewhere within 100 meters or 150 meters span, there will be a very a special type of relay which is able to collect the information from a number of the neighbors. And again, it's theoretically a two-way process. It collects that information, consolidates that information, and transmits over a wide area network back to some central entity that is able to collect lots of information and also signal back out. This is the infrastructure that's being implemented in Detroit Edison. It's about a $150 million project. I think $80 million is from recovery funds. When I talk with Detroit Edison, and admittedly this is 6 months ago or thereabouts, they have no idea what its capability is in terms of being able to signal back out to from the controller back out to the load ends. Southern California has the same physical system, but have implemented it in a different way, and they give different statistics about the ability to control from the utility back out to the loads at the end of the system. But the latency estimates are between 45 minutes and 10 seconds. Now that's a pretty wide range of numbers to have to deal with. So the infrastructure is being implemented, but there's not a clear guide as to what people are going to do with this. One thing they're going to do is, one thing they publicize is collecting information so that you can go onto your computer and see what electrical energy is being consumed within your home in the last 15 minutes or whatever. And my thought is, great, people will do that like for about the first day, and that's the end of that. The true benefits are the ability to communicate with loads and have them respond in a way that will help the grid. But that doesn't sell, it seems, to the community. And so that's not what people have been thinking about or focusing on very much at all. So there's this infrastructure that potentially could be very useful in incorporating loads into power system control. But on the flip side, it may be that we are left with this white elephant. After you've invested $150 million, no one's about to rip it out and start again. So it could be that the next 20 to 30 years we're stuck with something that is ineffective. And this is called the smart grid. So that's that's my plug for some of the activities that are going on. If they had just given a small fraction of that $150 million to University of Michigan to do research, we could have made much better use of it. Okay, so what are the sorts of things that we can do potentially with being able to control the loads? So one thing that is possible is to look at what's called valley filling. So this is a typical summer load profile for the Midwest Independent System Operator. It's the regional operator. It covers Illinois, covers Michigan, out to the Dakotas. It doesn't cover Chicago, but anyway, this is 4 p.m. It's summer, so there's a lot of air conditioning. As things cool down, the load drops. There's a dip here as people come home, turn on lights, televisions, cooking, etc., and then it drops down overnight. With the large number of electric vehicles, we would like to be able to charge them in this overnight valley. And there's a lot of reports, a lot of papers that say just that. The type of situation is if we could fill this valley with plug-in electric vehicle charging load, that would make operation of power systems way simpler and way more economic as well. So people have proposed strategies that are, for example, time-based, where you don't expect the vehicle to start charging immediately that you plug it in, but there's a timer, so it won't start until, say, 10 p.m. after this load dip has passed. The sort of thing that one can easily show is that you can induce a second peak in the load. And this was produced from something like 2 million vehicles across the Midwest area, which is something less, it was roughly, I think, 20% penetration. I forget the exact numbers. The turn on timer is randomized between about 8 p.m. through till about midnight, and the vehicle amount of charge that they were required to absorb was randomized as well. But even with that, one still induces a second peak as there's some coordination associated or synchronization associated with the loads. Other strategies that people have spoken about are to look at a price-based strategy. So in this particular case, the strategy that we have implemented is to say that vehicles will start charging when price falls below a low threshold, and they will turn off when the price goes above a high threshold. So there's a hysteresis band that's built in to prevent chattering, and that works fairly well with a relatively small number of vehicles. As the number of vehicles grows, the gain in the system effectively grows, and you start to see some jitter until you can actually induce a bursting phenomenon. Again, there's the lower and upper thresholds are randomized. So for every study that you look, you don't necessarily always see that bursting phenomenon, but randomly it will appear, and it's due to a synchronization of the loads, where enough loads, where the price drops, enough loads see that it's now time for them to charge. They all start charging, that pushes the price up, and then they all stop charging, and you get this bang bang type phenomenon. The assumption underlying this is one of real-time pricing, and if you don't introduce real-time pricing, then you don't have this problem, but then you don't have the signals that people are talking about to drive this type of charging. We've looked at a different strategy, actually a Nash game-based strategy. And what we're saying is each vehicle wants to minimize its energy cost, and to sort of decompose this cost function. The P is the price of the total demand. It's captured in D, which is background demand, together with this average of what all the other electric vehicles are doing. Together that gives total demand, and the price is dependent upon that, and the U is the actual energy that's being consumed by the electric vehicle. So this is a standard price. This is what one would pay to their utility. To make this work, we have to add in a penalty for the individual plug-in electric vehicle deviating from the average behavior of all the vehicles. That becomes a cost function, and so then we're able to show that for an infinite population, so we're dealing with mean field theory ideas, if every vehicle minimizes this cost function relative to this trajectory Z, and if that trajectory Z is the average of all of the other vehicles, then that minimum that everyone achieves is a Nash equilibrium. We've been able to show that Nash equilibrium exists. It's unique. We can establish a convergent iterative process if this delta term is of a sufficient size. And if that's the case, then the outcome of all of these vehicles independently seeking to minimize their cost will in fact be exactly valley filling. If we don't have that delta parameter, what we find is a process like that, where all the vehicles detect at the time when the price is lowest is when they will charge, and there's an iterative process that's going on here. If I go back to this slide, to make this process work, we have a central entity that is collecting information about what all the vehicles are doing, and so it provides this forecast of the background demand, and it generates this average behavior based on what all the vehicles are doing, creating this Z vector or Z trajectory.
So I just have a question. When you say demand under the infinite population, whether that demand is going to go to infinity, because you cannot have that.
Yeah, and the little c here is a scaling factor. So the assumption here is that we're not at infinite, but the larger the number of, you need a larger grid to support larger numbers of populations of vehicles, and so the C is the generation capacity, and so it's the load normalized on the basis of generation capacity. As the number of vehicles approaches infinity, we're saying, well, that implies you need more and more capacity as well. So the normalization still gives you a finite number.
But isn't the price dependent on the total demand instead of the normalized demand?
The price, one can normalize the price function as well.
Okay.
Yeah, so the more capacity that you have, the lower the bids would be, and so you can normalize that as well. We can talk about details later. Okay, so it's this iterative process. One has a central market entity that's collecting all of the information that all of the vehicles are producing as they work towards minimizing their cost relative to this Z trajectory. This central entity creates the new Z and communicates that out or makes that information available. The plug-in electric vehicles will then minimize their cost based on this new Z, and that process will iterate. If we don't have that penalty term, that process will not converge. And the reason being that price is low, so all the vehicles decide to charge. On the next iteration, the price is now very high in this middle period, and so all the vehicles decide not to charge. Then they decide to charge on the side lobes. And then on the next iteration, that price is high, and so you can see the iteration. If one introduces an appropriate value for that penalty delta term, and that penalty need only be very small, then the process is convergent, and it's convergent rapidly. So typically, well, it depends on the value of delta, but for a reasonable value of delta, it will converge in 4 or even less iterations. And the actual penalty cost, if one assumes a homogeneous population, then at convergence, the term in the squared here will actually go to 0, and so the penalty will disappear anyway. The cost penalty will disappear at convergence. Not all vehicles are exactly the same, so in a heterogeneous population, there is some cost that's associated with this final penalty term. But if they're all close, then that cost is very small. And the convergence.
Will the result of that be some sort of mixed strategy of randomization, or no, it's just a schedule?
It's a schedule, yeah. So this would sit in the day-ahead process, for example, or it's based on forecast information, and then the plug-in electric vehicles themselves now say, okay, that's what I've promised to do over the next 8 hours, 24 hours, whatever period it is. And there's then some mechanism to ensure that they actually do follow that. So that's a great point, because it leads on to the next point, that this establishes a baseline strategy for each vehicle to follow, and that will give this valley filling condition. But then the system changes. So how can one incorporate into a responsiveness into the vehicles so that they can deal with things like fluctuations in renewables, loss of generation, et cetera, et cetera. So to do that, we have proposed this hierarchical structure. The idea being that the loads, we can't communicate centrally with every individual load. And in fact, even by introducing this aggregator level, the philosophy that we've adopted is the aggregator can, what we would like to achieve is that the aggregator sends a common signal to everybody. They interpret that signal in a way that is specific for them, but that the overall behavior has a desirable form to it. And we've been looking at structures that say the load aggregator sends or makes available a common signal. The load aggregator may be measuring or receiving information from a larger number of vehicles. It might be from everyone, it might be from a random sample of vehicles, but that there's ability to draw more information back about the loads, and this is to do parameter estimation, to understand the model for the load. So the load aggregator is pulling in sufficient information back from the loads, but is signaling a common signal out to all of the loads. The load aggregator then is communicating with the system controller in a way that looks to the system control like it's just another generator, for example. And so it can bid into the market, it can provide whatever services are required by the overall system. The general philosophy is that we have to deal with competing objectives. The individuals have certain things in mind with their loads. If it's an air conditioning load, each consumer wants to have their temperature about the right level. If it's an electric vehicle, they want to have their vehicle fully charged by the time they drive to work the next morning. So there are local control objectives, but then there are system service requirements or desires as well. You want to be able to balance renewable generation, for example. We also, this philosophy is to ensure there's a consistency between, with the legacy power system operating philosophy. There's an enormous amount of infrastructure that's not going to go away. So we could propose exotic control schemes, but they would never actually be implemented because system operation is not going to change that much. And then finally, just that the centralized control of large numbers of loads is impractical. So my colleague Duncan Callaway has done work on thermostatically controlled loads. He looked at air conditioning, and this is a standard model for the temperature behavior with air conditioning turned on or with it turned off. It just describes the temperature increase when there's no air conditioning, temperature decrease when air conditioning is on. And for a large population of such loads, one ends up with a probability density that has this form. This lower curve shows the density associated with on loads and the other one with off loads. And the control strategy is that if I want to increase load by a small amount, one way of achieving that is to just shift the deadband. So I set my temperature, but that temperature has a deadband around it. And the actual air conditioner will turn off when it reaches the lower end of the deadband. It will turn back on again when it reaches the upper end of the deadband. If I move the deadband just a little bit, so if I want to increase load, I can change the set point. I just lower the set point a small amount. What that means is that the air conditioners that were off and about to turn on but hadn't quite reached the upper threshold, temperature threshold will turn on a little prematurely, a little earlier. The air conditioners that were about to turn off because they were about to reach the lower threshold, they will stay on a little bit longer. And by messing with the loads at the ends of the deadband, that gives quite a good deal of controllability associated with the total aggregate load that comes from all of these thermostatically controlled loads. From an individual's perspective, they're not really seeing very much of a change in temperature. In fact, this slide shows that in order to track the output of wind generation, which is varying between about 100 megawatts up to 180 megawatts, the variation in the temperature set point for 60,000 air conditioners, the nominal value was set to 20 Celsius, and the deviation was the maximum deviation was about 0.1 of a degree Celsius. So the occupant's not going to notice any difference at all, but given that variation, and this is a common signal that is broadcast to all 60,000 air conditioners, that gives sufficient change in the load that the load can almost exactly, this is the error, almost exactly track the fluctuations in the wind. So that's air conditioning load, and there's a number of variations on that same theme of messing with the loads that are close to the edge of the deadband. We've taken that idea and looked at ways of applying that for electric vehicle loads. with an electric vehicle, the important parameters are that you have a certain turn-on time, you have a certain time when the vehicle has to be charged, and a certain amount of energy that needs to be acquired. In this figure, we have shown that as being just a straight line, but it could be the trajectory associated with what I find from my Nash game a little earlier. But it's just, from an illustration point of view, it's simpler to have a straight line. The way the charging works is that the charger will turn on until the state of charge reaches an upper threshold, at which time it will turn off, until it reaches a lower threshold when it will turn on again. And the black shows the on-off sequence for the charger, and that's associated with this jagged state of charge trajectory that one sees in the red there. So how do I go about controlling the total load? Oh, and I should say for 20,000 vehicles with this strategy, this is what the total load looks like for those 20,000 vehicles. Okay, if I want to control that total load, I can introduce a change, a small change in the deadband, and this little kink here is a change that I've introduced to provide some controllability. The outcome of that little kink, and it's not a very significant change, is shown over here. So you can, let me go back, that's without, so that's the total load without that small control. And then when I introduce that, I find that I get an initial step change, and then there's a transient response that follows that. So that suggests to me that by making changes in this deadband, I can get a good deal of controllability out of that load. And a simple little illustration that we've tried, this is kind of new work and not published, and things we're playing around with. So we wanted to force, if I go back, we wanted to force this load to follow, to track a nominal trajectory, an increasing ramp, and then hold constant. So we were able to do so with a very simple control strategy. The actual control input is shown up here. This figure down here shows the uncontrolled behavior at one of the 20,000 electric vehicles. And when I introduce the control, you can see that there's a deviation. The deadband has moved away from where it was. Okay, that's the nominal deadband, the dashed green lines. It moves a little. In doing so, it moves the on pulses. So again, if we take a look, here are the on pulses associated with the uncontrolled process. And after I control, I just move those pulses a little bit. The same amount of energy is being delivered over the same time period, but we're moving it just a little bit to achieve some controllability here.
Was it a global control for 20,000 vehicles, or you were modulating that?
So there's one signal going out to all 20,000. So every one of the 20,000 vehicles is seeing that same control.
And does your model assume that all vehicles are identical? Or?
No, it's randomized. So there's
The slopes with which they grow and decay are different for everybody?
Yep, they are. And there's some interesting, there's a lot of interesting things that are yet to be explored with this. But if I go back, depending on the size of this deadband, I can get a much faster pulse train, and so I can increase the speed of dynamics of the system, or slow it down, or do all sorts of interesting things like that. So please don't go publishing this before we do. But anyway, well, if it does, just gives acknowledgement in the right place. Okay, so where do we want to use these ideas? We have just received an ARPA-E grant. Well, we're in the process of negotiating an ARPA-E award, which is why no research is getting done anymore, because of ARPA-E's modus operandi. But anyway, the idea is what we're calling energy positioning, We're looking at developing control techniques that position energy both to achieve economic outcomes, but also to make that energy available to be able to deal with contingencies that happen in the system. And so we're looking at this three-level strategy. Level one, and there's some consistency, again, with the existing operating paradigm. Level one is consistent with unit commitment, where one's dealing with looking far enough ahead that you get the right resources, the right generation resources, the slow devices to come onto the system. You get them on at the right time in the right place. That establishes a nominal trajectory associated with the longer term forecast. And we're saying, well, this would run every 6 hours to update the forecast. And level two is consistent with unit commitment. It's a simpler problem in a sense that we're saying these are the resources that are available to us. How do we best utilize these? The difference to unit commitment is that unit commitment is looking at a single point in time, and we're proposing a strategy that is akin to model predictive control of, again, using a forecast over a shorter period to ensure that we get the energy in the right places at the right time, taking into account the best information available for renewables, the best information available for what loads and generation are going to do as well. Why do we need to do that? Well, with energy resources, so storage, you need to be looking ahead and making sure you've got that storage being scheduled at the right place, at the right rate, and so forth. And then at the lowest level, level three, there's a continual monitoring for violations, and if there's a violation, that's where we will use the load control ideas along with being able to pull energy out of storage to be able to deal with those contingencies before they start to cascade. So if you have a line outage, you can alter the loads, the energy storage, to unload parallel feeders. That can provide you with a fast response, and which will allow you a sufficient time to reschedule generation to minimize overloads. So there's a feedback process, there's a feed-forward process from each level, but there's also a feedback process. Change of status goes back to this middle phase. Change of model goes back to the upper phase. And so there's these interactions between all of these things. The basis of the control that we're thinking about is model predictive control. The issues become, how do you do that across a very large scale system? So we're looking at, we will be looking at methods of decomposing the MPC problem into a regional basis. So I'll just give some advertising that I am looking for 2 postdocs. If anybody is about to graduate and would like to get into this hot topic called power systems, or dare I say it, smart grid, there are 2 postdoc positions available at University of Michigan, assuming we can survive the ARPA-E award negotiation process. Okay. The type of thing that one can, type of outcome from this control strategy is shown here. This is what's called voltage collapse. It's just a simple little 10-node power system, but it's one of the standard voltage collapse test systems. When there's a particular feeder, when that trips out, if there's no control, the voltages will deviate. This is pre-fault, the voltage is above 1 per unit, which means everything is nice. When that line trips out, the voltage drops to about 0.95, and then tap changing transformers start to tap, and as they tap to try and restore voltage to the loads, they actually push the voltage further down rather than actually raising the voltage. And so one ends up with this degraded voltage down to levels that are unsustainable, and in fact there would be a cascade that would result from that. We have applied MPC in this case. The MPC runs on a 50-second cycle, and so you see initially these so there's some inconsistency between the plots, but these are voltages at some of the nodes within the system. They start to decay. MPC changes some loads, and this is the load change that's occurring. At time 50 seconds, it removes 10% of the load at one location, and it removes about 6% of the load at a different location. And that's sufficient to restore the voltages, but it actually overshoots. And so at 100 seconds, it puts all of the load back on at that second location. It takes a little bit more off at the first location. That restores the voltages back to their ideal values, and the cascade has been prevented. So this is the sort of concept that we're exploring, and we will explore more, and we need to aim for larger systems than 9 buses. One of the things that that this slide illustrates is that power system behavior is hybrid. So this looks like it's just a staircase down. There's actually continuous dynamics associated with generators here, but what you're predominantly seeing is the voltage that steps every time there's a tap change in the system. So there's an interaction between continuous dynamics and discrete events. And that is typical for power systems. It's unavoidable in power systems. So we have looked at a model that we call this differential algebraic impulsive switched model that captures the standard differential algebraic representation of power systems. So here's the differential equations, the algebraic equations. It incorporates switching into the algebraic equations. So different sets of equations will be operated upon depending upon the values of certain triggering states. And it also introduces impulsive behavior such that when this trigger is encountered, then the states will undergo an impulse based on this function h. And so it captures all of the dynamics that we have needed to be able to capture. And I suspect it is fairly generic, though I've never sat down to really think about how generic the model is.
So in this case, do you have bounds on state variability?
No.
Inequality between
Well,
you don't have
it depends totally on what your dynamic models are. So if you have a model that has a saturation limit, that saturation limit will be, oops, where have I gone? Got it. That saturation limit will be taken into account here. So you will switch, so say it's a non-wind-up limit, then you will switch from the dynamics associated with the input to that block through to the state remaining constant at the non-wind-up limit. We can talk some more about it later. So this is a model that is very much amenable to simulation of large-sized systems, and in fact we do that routinely. The other aspect of this model is that it allows trajectory sensitivities to be computed efficiently. So what do I mean by trajectory sensitivities? It means I can determine to a first order approximation how does my non-smooth trajectory change, how does the entire trajectory change for a perturbation in the initial conditions or parameters. And so then I can use that in a variety of different ways that I won't get into in too much detail here. But the trajectory sensitivity is a linearization around a nonlinear, non-smooth trajectory.
The Y here is generated exogenously, or is part of
No, it's an algebraic state that's coming out of the algebraic variables. Yep. Yeah, so there's no exogenous inputs. Okay, so just an illustration of the type of thing that this model can capture. This is part of a wind turbine model that's used in industry. It's industry standard, And you will see there's all sorts of non-wind-up limits. And in fact, there's some really interesting interactions. When this block here hits its minimum or maximum limit, not only does that create the usual non-wind-up phenomenon on the state associated with that block, but there's a signaling over to this integrator and to that integrator that they should block as well. And when it comes off that limit, then the signal says these integrators should come off. And in fact, one can show, and we have shown, that this introduces deadlock behavior. So this model is not actually, cannot actually be simulated using traditional simulation. How does industry do it? They use really bad numerical techniques that come out of the 1970s and that don't properly implement the limit switching. When you properly implement the limit switching, you need Filipov solution types of phenomena to be able to continue the trajectory. It's like a sliding mode phenomenon. So the type of thing that happens, again, this is associated with this model documentation is a standard case. And when you look at the standard case doesn't work. And in fact, what one finds, a way of overcoming this is to introduce a hysteresis threshold. If you don't have that hysteresis threshold, you can encounter the type of thing that happens is if the error signal into here is increasing but negative, as it increases through the proportional gain, it can pull the output state off the lower limit. When it pulls the output state off the lower limit, this integrator becomes active, but the error signal is still negative. So depending on the relative values of these gains, it pushes it straight back onto the limit. But when it's on the limit, this integrator is blocked, so it comes off the limit. And so you can see the type of thing that goes on. And the way of overcoming that is to introduce a hysteresis band, and then things work properly. But without properly modeling the hybrid dynamics, one doesn't see these things. And the industry standard models, in the power industry at least, the industry standard simulation packages do not implement limits properly, and so they have not noticed these things. Okay, so that then moves me on to not only are hybrid dynamics important in power systems, but one really needs to kind of couple in the cyber infrastructure. And this is where this is very new to us, and this is where I personally struggle to really get that model right. So one approach that we have taken, modulo without any simulation results yet, but with the math cranked through, is to capture the effects of latency in the process. So the simple example, I'm not sure how realistic this is or not, but to say there's some crucial feeder that trips and adjacent feeders overload. So now we would like to be able to schedule loads or reschedule loads to be able to deal with that. So we start signaling out over our communications channel to the various different locations that should be active to prevent this overload. The increased activity on the communication system increases the delays through the communication system. And so we've looked at an arbitrary kind of representation of saying over a certain range, traffic volume as it varies, it doesn't alter the delay at all. But then as we start to increase that traffic volume to higher levels, the time delay increases as well. And I'll be interested to talk with people as to whether this is a reasonable assumption or not. But the math's interesting anyway, so why not? So that's the sort of model that we're looking at. It doesn't have to be a single input, single output. It could be multiple, multi-input, multi-output representation between traffic volume and time delay. But what we're saying in this maybe naive example is that we get this increase in communications time So there are delays in the response of the loads, but then there are delays in the SCADA system as well. And due to that, we lose controllability and observability of the system. And there are further overloads and a cascading failure, and the cascading failure is inherent in the increased activity and the delays that are coming. This is something we really have to think about in terms of our ARPA-E, because we're saying, one of our justifications for that was that maybe we can move away from the N-1 criterion, which costs us some money, to looking at faster control to be able to have a control-based solution. But if I'm relying on that control-based solution, I better understand the latency issues pretty well. Okay, so this model can be incorporated into our differential algebraic impulsive switched model. And we can incorporate that in a consistent way. We can generate trajectory sensitivities as well. So what does that allow us to do? Well, we can start to ask questions about, well, what happens if I vary this switching point here? What happens if this slope is different? Those kinds of questions. Okay, how does that show up? This is some work not in terms of looking at latency uncertainty, but looking at uncertainty in other parameters. This figure shows a nominal trajectory in state space. That's the blue curve, and then we have mapped along with that using trajectory sensitivity an estimate of the uncertainty in the parameters. And so one can get a bound which says nominal trajectory is this one, but if I want to take account of all of the uncertainty, then I need to be dealing with the outer limits of this behavior. In the time domain, it shows up in this kind of way, that we have a nominal trajectory, but then we have a bound that sits around that nominal trajectory. And we can ask questions about, well, it turns out the zero crossing here is a significant event. It's a protection operation event. The nominal trajectory does not cross zero, and so if I was just running the simulation, I would believe that everything was great. But in fact, if I take into account the uncertainty and parameters, then I really do see that there's a finite probability of encountering a protection operation which may incur maybe the start of a cascade. This is all non-linear, non-smooth. You can see the switching that's happening there, and it provides us an ability to get an approximation to this bound, but not the exact bound. Okay, so in conclusion, I've sort of wandered a convoluted path a little bit, but let me just conclude by saying there's significant actuation that's available from coordinated control of loads. There are issues associated with that in terms of what's the right control structure, how do I deal with latency, interoperability, data security, all of these things we've heard about through this symposium. But there are social issues as well. What are the incentives I need to provide to consumers to participate in fast acting? It's non-disruptive. They don't even know it's going on. But in the consumer's mind, they really don't like their utility, so why should they help their utility? And so what incentives are required to make consumers or help consumers understand the benefits? Thank you.
Thank you, Dr. Hiskens. Questions, yeah.
Can I ask you a question about that incentives? Because when we looked at this, it's cool to look at how you can use the load as a control. But then when you get into how much you would have to pay someone versus the amount of gain in the sense of benefit you're getting from each individual load, we're looking at pluggable hybrids, using it for contingency controls. And you have to pay people, a couple cents at least, or 50 cents to get them to plug in their car. That gets really expensive when you get such a little benefit from each one of these controls. I know you're not a real dollars guy, but did you look at this?
No, not at all. So in the ARPA-E, it's myself and Dan Kirshen from Seattle, and he's the economics guy. That's my cop out anyway. No, I haven't looked at that at all. And it's a really difficult number, because you really have to then say, well, can I actually avoid the N-1 criterion? Can I use load control to save what it was going to cost me to build new transmission or to operate generators in a certain reserve regime, and that's a really complicated economic analysis to understand. So the issue of how much do you pay, the issue of how much do you pay is based on doing surveys of consumers. The issue of is it worth it, that's a much more difficult question to ask.
Just a comment, as well as getting rid of the word smart meters, can we all agree that we will never use the terms price signals? Because in this field, people use the term all the time, and immediately we know it's not going to work. We know that the uncertainty of news for the consumers, and the issues that you've talked about, we know we're not going to do that. So we should really just forget all that. This will be done through some contracts.
Yeah.
Slow time scale, but it's just.
I agree. Using price as a control signal is like, let's add as much noise and as much uncertainty and as much nonlinearity into the system as we possibly can, and then see if we can do anything with it. and
Any possible value that's.
yeah.
So if you add these AMI systems to every home, neighborhood, and city, won't it use a lot of extra power? So if you consider in the Midwest, for example, would you need to build an extra power plant to implement this?
Again, I don't know how much these new meters actually consume themselves. So I don't know the answer to your question. I don't think it's a huge amount of extra. The computation and the communications are not as much as in a server farm, for example. And a server farm's like 60 to 100 megawatts. So, but I mean, how big a scale are you looking at? I haven't looked at that at all, but there's something to think about. Yeah.
Just a comment on the incentives question. I think the part where you discussed charging of electric vehicles, it somehow assumes the fact that there's the residential customers who are the owners of those vehicles. They are subject to demand-based sort of pricing, which is not the case right now because the majority of residents are built on a fixed pricing. They don't have any incentive to reduce their load because they will pay a fixed cap at the end of the month, irrespective of their peak demand. So if there is a change in the pricing paradigm and they are also subjected to peak power pricing, then there's already an incentive for them to reduce their peak, and then these sort of strategies will come into play.
The plug-in electric vehicle loads are really interesting because if there's no controls, you have 2 or 3 houses connected to a single transformer. They all decide to charge. They kill the transformer. So there will be a need for utilities to somehow coerce participants or plug-in electric vehicle owners to establish some coordination, at least locally. And if they're moving in that direction, then hopefully it's not such a big further step to say, oh, and by the way, not just solving these local issues, but there's an opportunity to be able to deal with much larger issues as well. But I'm a technical guy. I love playing with the control ideas and the math and stuff, and the practical stuff. Yeah, Tom can work on the practical stuff.
Yeah. We're also looking at similar stuff, and we love the technical part. But when engineering intersects with economics, then you have to think about all this stuff.
Well, and it's not. It's when it intersects with social behaviour. That's when it gets really complicated. I mean, the economy. Yeah. I agree. It's challenging. Yeah.
More directly now, Professor Rowe, these questions on incentives. Some of the incentives of having control on the loads are more long-term, and that would probably be a better reason to give them some more dollars for having the flexibility to control them. For example, you could probably do away with some upgrades on the distribution system or on the transmission system, or even not have the need for
I agree, but there are also short-term benefits as well. Yeah, yeah, yeah.
The slide on which you showed following the wind variations, I was wondering what is the class of signals that you can track with your control if you consider an error band that you want to meet and a certain delay.
What do you mean by class of signals? What?
Can I just have any arbitrary wind generation pattern with a still work?
No, you can't. There's a really interesting nonlinear phenomenon that the controllability is coming from moving from altering the status of the devices that are in the edge of the deadband. If you think of a jitter type phenomenon where you move back, do that a couple of times, the underlying dynamics of the air conditioning won't necessarily have replenished those end pieces, and so the gain that you have the first time you make your control action will not be the same as the gain you have the second time. So if you start to try to do fast control, well, the rate of control is tied back to the underlying dynamics or the speed of response of the underlying devices. So there's those sorts of limitations that you need to think about. Did that answer your question?
I can talk about it a little later.
Okay.
The question that I had was, so you publish a general control signal and rely on the other guys to interpret it correctly. So let's say you have 50,000 vehicles and 50,000 air conditioning units, and 25,000 of those each decide to disobey you. How does that affect your performance?
Yeah, so one of the things I haven't talked about here at all is the model identification process. So inherent in being able to use 60,000 air conditioners as an actuator is having some model of the response, and that's going to change from time to time. If it's a hot day versus cold day, if it's midday versus evening, you've got all of these variations, and so one needs to have a process of being able to signal out with maybe a pseudo-random signal to be able to estimate the parameters in a continual manner. And then if you're doing that, then you're picking up on who are really responding and who are not responding. So there's some will claim they're responding but not. And and maybe that process, if people are being paid for the service but they're not providing the service, you need to have a mechanism determining who is actually doing the right thing. So again, that maybe that model identification process is also being used to determine who is really responding and who's not. But there needs to be that online adaptive scheme that's going on.
Let's thank our speaker again. We're going to take a break now, like for 10 to 15 minutes. So if you had more questions, you can just take them offline. Yeah, let's thank Dr.
Thank you. Okay, thank you. Thanks.